Today we're going to start reviewing for our quiz. Our quiz is going to be on Tuesday. So three main topics, trig derivatives, trig related rates, and inverse trig derivatives. So we most recently saw related rates and inverse trig. So today I just want us to focus in on trig derivatives, and Monday we'll do another day review, and I think I'll have a more complete review there. Okay. But let's start with number 1. I just want to make sure that we recognize the methods involved. Give you guys a chance to try the problem. I'll display the rules, and then I'll spend time going over each problem after you guys had a chance to try it. So here's number 1. Find the derivative of x cubed secant of 7x minus 2. Okay, look at how this problem is set up. What do you see here? What's involved for the derivative process? Good, right? So product rule is not hard to apply, but sometimes it is hard to spot. So in this case, we need to be able to recognize product rule when we see it. Yeah. Okay, let me display the rules and then have you guys try it. If you get done with one, feel free to move on to the next problem. Okay. Okay, let me go through the steps, see how you guys did. So treat my first term as f, my second is g. Go through product rule, f prime, x cubed becomes 3x squared. We keep the original g function, back to f. And then g prime is asking for secant's derivative, and secant's derivative is secant u tangent u times u prime, so we're just applying that step here. So secant parentheses, tangent parentheses, and then the derivative of what's inside the parentheses, which is times 7. Okay, you can leave it in this form. I'm just pushing the coefficients out in front. That's my preference, but any version of y prime is good. All right, any questions with one? Take a look at number 2. What do you notice? What's involved here?
Quotient.
Yeah, quotient rule is a little bit easier to spot, right? That numerator denominator kind of gives it away. Well, try that. Yeah.
Could you combine in the first problem the secant and tan to be like 1 over cos squared or sine over cosine squared?
Yeah, that's fine. You can do that. However, I will say that if this was a multiple choice question, this is probably the form that's gonna look most like it. But you know, if it's free response, any version is fine. Yeah. Okay, number 2, your derivative will look a little messy, but that's okay as long as you have some version of the derivative. Okay, so sine of 3x is my f. Denominator is my g function. So sine of 3x becomes cosine 3x times 3. Keep the g, keep the f, and then g prime. Cotangent's derivative is negative cosecant squared u times u prime. This form is fine. I clean it up by taking the 2 negatives, converting it to a positive. And my preference is I like to push coefficients out in front. So that's my. Okay, any questions with 2? I do want to make a note about notation here. This is very subtle, but I think it's important to point out. This is the shorthand way of representing that cotangent is being squared, right? But you can also write it in this form with brackets, which is what I would prefer when we're getting ready to find the derivative of chain rule, right? But this is the way that most students will want to write it because you don't have to use as many brackets. But these mean the same thing, right? These mean the same thing. However, this is different. Okay, if that square is just here, then I'm just squaring the expression inside the cotangent, but it's not squaring the cotangent itself. So this would not be appropriate to represent that. Okay, so these two are the same. This is different. Okay. All right, does anybody still need to look at number 2? All right, let's look at number 3 here. Okay. Find the derivative. What do you see here?
We have to use chain rule.
This is chain rule. This is a function within a function within a function. Normally, chain rule is not that extensive, but with trig functions, they are. So because of that, what should we do before we jump into our derivative set? What should we, is there a way to rewrite this problem?
Brackets.
Yeah, let's put brackets with that 5, right? We have 3 different parts we got to work through with chain rule. It's a lot easier to spot it if that 5 is in a more helpful spot. Okay, from here, we need to recognize that there are 3 different parts to this problem. There's the outer side and there's the inner portion. Identify those 3 pieces, and then we're going to take turns with each derivative, and they're all going to be outside of each other. Okay, your derivative will be pretty long and pretty messy. I think the tendency is students want to try to clean up their chain rule and they want to insert the derivative within each other to make it cleaner, but that's not going to be correct. Okay, so just understand that with chain rule, it's just naturally just going to be a little messy, a little long. All right, try that. Okay, let's go through number 3. All right, so we need to be able to identify the 3 different parts here. We got the 4 bracket to the 5th. We have the cosecant parentheses. And then finally, we have that 4x cubed minus 2x. And we have to take turns with each of these derivative. Okay. All right, it's going to take a little bit of room here, so I'm going to put it in this space above. Okay, so first up is 4 to the 5th. Think of bracket as just a large variable. So we just do power rule here. Bring down the 5, subtract 1 from the exponent. So we get 20 bracket to the 4th. Now, when you take the outside derivative, you don't change the inside. The inside is going to just be duplicated. So copy everything you see inside back in. So that takes care of the outside portions derivative. Okay, good so far? Now we're moving on to cosecant. So cosecant has its own rule, which is negative cosecant u cotangent u. And the u is just the original inner portions, inner portion inside the parentheses, times negative cosecant of u cotangent of u. So that takes care of this portion's derivative, and then we stick the 4x cubed minus 2x inside those parentheses, because we're not ready for the inside just yet. Okay, we took care of this derivative, and now we're ready for the innermost portion, which we do power rule. So that becomes 12x squared minus 2. Okay, but just to help with order of operations, let's put that in its own set of parentheses. Notice that we don't stick each derivative all inside this box here, right? They're all going to be kind of sprawled out. Okay, any questions here? So this is fine. I like to clean up if I see that it's not too much trouble. So I'm putting and algebra out in front. Cosecants here I can merge together to be cosecant to the 5th. And that's what I did here. But this is fine if you would leave it like that. Okay. Any questions with these extended chain rule problems?
Could we just leave it in the above form? We have to condense.
This is fine. This is fine. Yeah. Mm-hmm. Yeah, I want to show you the condensed form here because if it was on the AP exam, this is what it would look like if it's multiple choice. Let's go to number 4. All right, secant of y is equal to 2x plus y minus 12. We want to find the derivative. All right, what's involved here? Good. You see y is kind of mixed into the equation. It's not y equals. And also there's multiple y's here, so we got to keep track of our dy dx's, right? Okay. So as a reminder, when we do implicit differentiation, we take the derivative of everything we see in front of us, but as soon as we come across a y's derivative or a derivative with y in it, we have to make sure we include and attach a dy dx. And the reason why is because these y's are dependent variable, with x being the independent variable. And so the independent variable is going to kind of leave kind of this residual impact with these dependent variables. So we're going to be expecting some dy dx to show up. And another thing to keep in mind is that if you count how many y's there are in the equation, that's how many dy dx's is going to pop up in your derivative line. All right, so try that. See if you're able to approach each derivative and include dy dx when there's a need for it. All right, let's go through these steps here. So we have a rule for secant, which is secant u tangent u times u prime. So we're just going to follow the rule here. The u is the y. So it's just going to be secant y tangent y times, and then y prime is where that dy dx is going to pop up. Okay, 2x just becomes 2. Y becomes 1, but then we need to attach dy dx because we're asking for y's derivative. Now, I like to put a 1 here because later, when we factor out the dy dx, that 1 is going to show up as a remaining term for that place. Okay, what about this 12 here?
It just
Disappears, right? Either put -0 or just ignore it, right? But we don't. Okay. So we got two dy dx's to show up, just like what we expected. And now I'm just going to move some things around, right? The derivative process is done. I'm just trying to get that dy dx variable to be by itself. So subtract the 1 over to the left. Okay, factor out the dy dx. And then we're just going to divide this over. Okay, any questions with 4? All right, take a look at 5. There's 2 things that stand out. What's needed within the derivative process here.
Product.
Yeah.
And implicit.
Good. Product, it's always hard to spot, right? But we need to see it, that they're two separate expressions. They're being multiplied. That's where product rule is going to come into play. And again, implicit because you have y's all over the place. All right, try this one. Does anybody still need to look at number 4? Let's see how we did. I'll go through the steps. Okay, so first up, f prime times g plus fg prime. So x stays, and then sine y's derivative becomes cosine y. We need to include that dy dx, right? Because this has a y in it. 5y becomes 5 dy dx. 2x cubed becomes 6x squared, and 10. Careful, we don't keep that 10, right? That 10 is going to turn into a 0. Okay, so there's our most important step here, because after this, we're just trying to rearrange and clean up. Okay. I have two dy dx terms. I'm going to leave those two on the left. The non-dy dx terms, I'm going to move over, subtract over to the right side, factor the dy dx out, divide the parentheses over. Okay, any questions? Does anybody still need to look at number 5? All right, good. Number 6, take a look at 6. What do you see? Another chain rule, right? Which means that we have a function within the function. What should we do before we start our process? Yeah, let's get that bracket, right? And what would you put outside the bracket?
1/4.
1/4. Okay, good. Start there. Okay, just like number 3, we want to identify the different parts. That.
Oh, so you have this. Yeah, that's not reference. Read it there.
All right, good. Looks like you guys are on the right track here. We have the outside portion being the bracket to the 1/4. The inside is the cosine, and then the inner is that expression 3x cubed minus 6x plus 9. We take turns with each derivative. and put them outside of each other. So first up, 1/4 bracket to the -3/4. Keep the inside intact. Next up is cosine, sine. So negative sign, keep the original expression inside the parentheses. And finally, we're ready for the innermost portion, which is 9x squared minus 6. Leave that in a set of parentheses, so order of operations is clear. This form is fine. I like to clean up, so I'm going to push this down to the denominator, make it share the same space as the 4, and then I have this in the numerator. And questions with 6. All right, anybody still need to look at 6? No. Okay, so there's one more thing I want to do, and I want us to do a related rates problem. I want to make sure that we don't forget the steps. So we may have done this already, but if we have, we'll just do it again. This is off the handout, the 10 problem handout with related rates that we did on Wednesday. So let's look at number 10. I forget if we've done it before, but if we have, let's just try it again. We have? We haven't? Okay, good. All right, so either pull it from your packet or you can just work it directly off of what we have here. All right, let's read the problem here. A model rocket is launched 30 feet from Maria, rising vertically at a constant rate of 20 feet per second when the rocket has an elevation of 40 feet. How fast is the angle of elevation changing? Okay, so with all these related rates problems, we're going to be involving d theta dt, but let's build our triangle first. Okay, so Maria is standing here, the rocket is being launched here. So we know that this distance between the launch pad and Maria is not going to be changing, so it'll stay 30. However, the rocket is still moving, so we want to make sure we don't put a constant here. Even though we have a y value, we know that as the problem progresses, that distance is changing, so we want to let a variable represent that height. And then the angle of elevation is this theta here. Okay, so there's our starting point. Okay, next decision we have to make is which trig function is best suited for what we have in our diagram. Tangent, right? There's nothing, no information about hypotenuse, so we have adjacent and opposite, so tangent is the best fit. Opposite over adjacent. I'm just going to do a little bit of cleanup here. It looks a little bit cleaner if I push that 1/30 out in front. Okay, we're ready to find the derivative. What is it about related rates that makes it unique in terms of the derivative? What's going to show up?
The velocity.
Okay, but in terms of notation though, what's the independent variable that's pushing all these terms here, impacting all these terms here? Okay, all will produce a what? A d over dt, right? Time is the independent variable. That's the thing with the related rate. So with implicit, it was x being the independent variable, and so the y gets impacted by dy dx. But with the related rates, it's always d over dt. Okay, so we find the derivative. Tangent becomes secant squared. One over 30 is the coefficient that stays. Y becomes dy dt. So let's go back and see if we can gather the rest of the information that we need. All right, go back to the problem here. 30, we already have that. Rising vertically at a constant rate of 20 feet per second. That's referring to the vertical motion, so dy dt, right? The velocity, vertical velocity there. We put positive 20, not because it's going up, but because this distance, this y is increasing. When the rocket has an elevation of 40 feet, so this is a moment in time, right? We don't want to include it at the beginning of the problem, but now that now we're just looking to gather some information here, a moment in time, 40 feet. How fast is the angle of elevation changing? So we're looking for d theta dt. So let's look here. dy, have that information, we're ready. D theta dt, that's ultimately our goal, which we're going to be solving for. But then there's still something that stands out, right? The fact that we don't have anything for secant squared theta yet. And so this is where our next piece of work is going to come from here, next piece of steps here. This is what makes this unique. This related rates problems requires us to do that extra step with that trig function. So that extra step is creating a second triangle with all the sides labeled. We can carry over some information. We know that this horizontal is 30. But now we see that this 40 is going to be helpful, right? Not before, because it's changing, but this 40 is going to come in handy because now we're zooming in on just a moment in time. Okay, we want to fill in all three sides. So what's the hypotenuse at this moment in time? 50, right? If you recognize this as a 3, 4, 5 triangle, you can make that adjustment, or Pythagorean theorem will always get you there as well. Okay. We're trying to find a suitable ratio for secant of theta. So based off of this triangle, what's secant of theta going to be equal to? Good. Remember, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is going to be hypotenuse over adjacent. And we can reduce that to be 5/3. Good. Okay, we should be in the clear now because we have all the information that we need to solve for our d theta dt. Okay, so secant gets replaced with 5/3. I'm make sure I square that. dy dt is 20. I'm just going to try to isolate d theta dt by itself. I'm going to divide the parentheses over. I'm also going to try to square it. So this becomes 9/25 times thirds. use your calculator, or you can just work this out by hand. I get 6 over 25. All right, and finally, what's our unit of measure? Good. Theta is always in radians, okay, never degrees. And then our time component is seconds, yeah. All right, just want to make sure that we don't forget the steps, right? We did a lot of it on Wednesday, but I want to do one before the weekend. All right. Okay, so Monday we'll do a full review with related rates, trig derivatives, and inverse trig. This afternoon, I'm going to have a help session at 3:30, face-to-face and Teams. It'll be recorded. If you want help doing test corrections, I'll do similar problems to help you with the steps. So Monday is when the assignments for the Chapter 5 recovery test is due, Monday night by midnight. Turn it in through Teams. Tuesday is our quiz, and Wednesday is going to be the Chapter 5 recovery test, either 7:15 or 4:30, depending on which one you choose, and it'll be on Teams, it'll be virtual. And then in class Wednesday, we're going to start preparing for the final exam. Okay, final exam is, you guys are all exempt from the exam, but if you take it, if it helps your grade, it'll be entered into the grade book. Okay, it'll be curved as well, just don't know what that curve is yet. Any questions? Tentatively, the final exam, 16 multiple choice, 90 minutes. Subject to change, but right now that's what we're looking at. All right, that's all I have. Hope you guys have a great weekend. See you guys.
Have a nice weekend, Mr. Yang.
See you. Have a good weekend.
Thank you.
Bye.